You can't explain it. It's electric chemistry. Yeah, I know. That was a good way to start, wasn't it? You liked that, didn't you? Yeah. Like I said. Alright, guys. So, first question here, standard galvanic cell. We have a lot of pieces labeled, but we don't know who's who. We have manganese and permanganate on one side, cesium metal on the other side, and we have a reaction. And so by looking at the voltages of the two reactions, we have to figure out which reaction to flip around. We have to flip one of them around. Right, Casey? You think we have to flip one of these reactions around?
Yeah, totally.
Because if we don't flip one of these reactions around, then the electrons are both on the same side. One has to be oxidizing, the other has to be reducing. So take a second, look at the two voltages, and we can see that the cesium one is the one we're going to flip around, because if you remember, the voltages need to be a total value that's positive. So 1.51, reversing this one, positive 2.29, carry the 1. 4.4 volt. Whoa, 4.43 volts when we flip this reaction around. So cesium needs to be releasing electrons. Undo that. So making cesium ions. But we do have a problem. What is the problem? Casey, are these two reactions have the same number of electrons?
Nope.
Which reaction should we multiply?
The top.
We multiply the top, though. It's already got 5 electrons. We want to multiply the second one, don't we?
Nope, it's the second one.
Right, okay. So, but a weird thing happens here, Casey. When we multiply this reaction, well, it gives us 5 times the number of electrons. We do not multiply the voltage. We just changed the amperage. We did not change the voltage. We changed how many electrons per second, not how far the electrons are falling, because it's still the same element. Okay? It's kind of a weird thing. It's kind of weird compared to Le Chatelier's principle. So which of these two reactions is losing electrons? Looks like it's cesium, right? So this is the losing electrons oxidation. The other one is gaining electrons reduction. And so our new silly phrase is A for anode, Leo, cat for cathode, GERS. A, Leo, cat, GERS. So the anode is the cesium side. Here we go. And the cathode is the manganese side. You might notice that there's a piece of platinum stuck into the manganese and permanganate solution and the hydrochloric acid solution. That is so that the electrons can be delivered, but the metal doesn't actually react. There are several non-reactive metals, such as platinum, that will deliver electrons without actually going into the solution. Like if you used alkali metal here, alkali metals would dissolve into the solution real quickly, so they're picking a metal that doesn't really go into water very well. I just also noticed that this reaction's not balanced. We have 4 oxygens, so we need to put 4 over here. That's 8 hydrogens. We need to put 8 here so that at least that part's balanced. And we could put all the pieces together afterwards to have the total reaction. These guys would all be on the reactant side. These would be on the product side, minus those 2 electrons. Just a second. These guys would be on the product side, and the electrons are equal but opposite, so they would be canceled out. In the hallway? There should be a wire to connect them. This wire is open. We better close it so that the electrons can flow. If the wire is open, then they can't flow. When we do our lab, we will actually have wires connecting the metals that are based in the solutions. Since the cesium is losing electrons, those electrons will be going up the wire now that it's closed, and then down through the platinum into the solution where the permanganate will change into manganese ions. So therefore the electrons are flowing this way through the wire. But remember the loop we talked about. If the negative is going one direction, we have to keep the negative charge flowing through the salt bridge. This is a really pathetic looking salt bridge. Usually it's a big U-tube type thing that's upside down. So the nitrate has to be flowing to the right through the salt bridge to keep the negative flowing in the same direction. All right, so what do we have here? Number one, when the current's allowed to flow, which species is oxidized? Cesium, which species is reduced? Manganese, label everything. Done it. Oh, didn't put the salt bridge. Here we go. This was called the salt bridge. It's called the salt bridge because it bridges what would be a positive-negative differential by filling it with a salt solution of some sort. Hey, Mr. Murphy, what's a salt? Any ionic compound dissolved in water that's aqueous, that breaks apart into its pieces. What occurs in the salt bridge? The cations and the anions flow between the two cells of the battery to maintain a neutral charge. And then we already actually did this one. What's the value of the cell? We combine the voltage together, so the cell potential is 4.43 volts. And what's the oxidation state of manganese? That manganese is a +7. It's going from +7 here to +2 here, which is why there's 5 electrons. So after all of that, do you have any questions about batteries, Casey?
Is that a cesium anode?
It is a piece of cesium stuck in there, which is probably completely illogical, isn't it?
Yeah.
Cesium's super reactive.
Why would we? Why not steel? You don't have to worry about it rusting, because wouldn't it be under a negative bias?
That's true. You could use other metals. We're trying to do simple galvanic cells, and we don't know I don't have the reduction potential between cesium and steel. Sorry. Okay?
Okay. When I was in Disney, I pretended that there was a miracle. Hi class, it's me, Casey.
All right. So as you probably tell, Casey was sitting in on the beginning of that. He's got to go home. All right. Number 7. If you increase the molarity of the permanganate, would the electromagnetic force increase or decrease? So you're thinking Le Chatelier's principle here. I have written the reaction all together, so these are my reactants. This is the products. And we already knew the voltage from the previous question. When you add reactants, when you add additional reactants, the voltage increases. And so adding permanganate should cause the voltage, EMF, to increase. I'm not going to have you calculate it, but just predict that it would change up or down. Number 8, if you increase the molarity of cesium ions are on the product side. By adding products, you would be decreasing the voltage. If you're using redox balancing skills, what's the coefficient for hydrogen? It would be 8. How many electrons are transferred? That would be 5. That would be important if you were doing a Gibbs free energy question. You'd know the value for N. In the whole delta G equals NFE, negative NFE. That 5 would be the value for N. It decreases as cesium. Oh, wait, I should read the question. What happens to the mass of cesium? This is an interesting one. What happens to the mass of the solid? This solid is becoming aqueous, and so if the solid is dissolving into the solution, we would expect its mass to decrease, and that's something we could actually verify by pulling the piece of metal out of the water and weighing it before, during, and after the battery was running for a while. Number 12, which of the following would be the best reducer? Remember, this means the best at gaining electrons. The best at gaining electrons. All of these elements are reduction reactions. And so we're looking for the one that's best at taking electrons. By looking at the voltages, we can see that fluorine is the most positive value. So it is the best at gaining electrons of these. That also fits in line with some of our old knowledge. Whereas you go across the periodic table, there's periodic table. As you go across the periodic table, the strength of the atoms increases because the effective nuclear try to write here so you can actually read it. The effective nuclear charge is increasing, but the shielding effect is not. As we go down the periodic table, we're getting extra layers of electrons, so we're increasing in shielding effect. So which element is ridiculously small in terms of shielding effect? That would be fluorine. Which element has a very high effective nuclear charge? That would be fluorine. It doesn't have a full valence shell yet, so of all the elements, it is the smallest and the strongest, which also is backed up by the extremely positive voltage value we have here. Copper would be oxidized by which other substances? So what we're saying is which elements would cause copper to lose electrons. Remember, losing electrons is oxidation. So of these elements, which ones are strong enough to result in a positive charge? Well, so you could do the math on each one. Fluorine is 2.87, forcing copper to be oxidized, negative 0.34. Put those together and you have a positive value. Therefore, fluorine is strong enough to oxidize it. So is chlorine. So is silver. But after silver, you then run into a couple of ones that would be negative values and therefore not strong enough. So that's the only three on this list. Determine the standard potential, E cell, for this reaction. You just look up the values, make sure you flip around the right one. This time we are flipping the iron. Iron's going from negative 0.4 to positive 0.44. So the voltage is 0.78. This time copper's being reduced because it is stronger than iron, so it's taking the electrons. Sorry. A common car battery consists of 6 identical cells, each of which carry out this reaction. I did some of this, talked about the car battery and how you have lead plates and lead oxide plates immersed in sulfuric acid. So first thing we should do, though, split this apart into its 2 reactions. So I did that in red. I split the lead in sulfuric acid from the lead oxide in sulfuric acid, and then you kind of go through and work out who's being oxidized and who's being reduced. The lead is going from 0 to +2. The lead oxide is going from +4 to +2. So there's 2 electrons being exchanged hands. Number 4, calculate the value for each such a cell is 2.04 volts. Calculate delta G for this reaction. Should it occur spontaneously? So we have to plug in the number of electrons. There were 2 electrons being exchanged hand in number 15. When the lead becomes lead +2, that's 2 electrons. When the lead oxide becomes lead sulfate, the lead is gaining 2 electrons. So the 2 lost equal the 2 gained. In either way, this N value right here becomes 2 to represent those electrons. F is Faraday's constant from your sheet. It's 96,485, I think. And then the cell potential was given as positive 2.04 volts. Do the math there. Negative 393,000 joules, or negative 394 kilojoules. So assuming that the wires are all connected together, this reaction should occur spontaneously, and that's what the key does. When you stick the key in the car and turn it, you're connecting all of the wires together, and then the current flows because the key has got all the wires hooked up together, and the current flows and makes the spark plug spark, or the gasoline catches on fire, and then bam, you've got a car running. Yay. 17. Why did he just whisper? I don't know. In 17, you have 125 amps. This is the amps for a car. This is not the amps for a battery. A car has a ridiculous number of amps, which is really, really frightening. This is why they say you should never, touch the positive and negative poles on a car battery, because the amount of current flowing is insane. So that is 125 coulombs per 1 second. That's the amount of charge per second. So that is our ratio of coulombs per second from the amps. It went for 15 seconds, so we can figure out how many coulombs. I, for some reason, have a rounded value for Faraday's constant there. It's 96,485. To change it to moles, as we said a little while ago, the reaction has 2 electrons being exchanged. So for every 1 mole of electrons, there's for every 2 moles of electrons, there's 1 mole of lead, and then 1 mole of lead is 207 grams. So if you turn your key and hold it and try to run the key for 15 seconds straight, you're using up 2 grams of lead from your battery. And that would be a problem. That lead is turning into lead sulfate, which may or may not be able to be reversed properly. And that's what slowly happens to a battery, is the lead sulfate builds up at the bottom and you don't get the battery to fully recharge. Question 18 kind of feels like it should be on a separate page because it is a drastically different question. But so here's the scenario. You are working in a factory and your job is to get magnesium that is dissolved in seawater and turn it into magnesium solid. And the common way of doing this is to force electrons into the solution, and the 2 electrons forced into the solution, the magnesium picks them up, turns into a solid, and then we can scoop the magnesium out of the water as it gains more and more electrons. So this is an electrolysis plant where the current is flowing, and your job working at this plant is to convert 1 million grams of magnesium. That is a whole lot. It's a metric ton. 1 million grams is 1 metric ton. Fun fact. So 1 million grams. Probably shouldn't use grams for anything ever, so let's change it to moles. There's the molar mass of magnesium. Now I know how many moles. Next step, every magnesium dissolved is going to receive 2 electrons. So now that I've got moles of electrons, I can use Faraday's constant to change moles of electrons to coulombs. And they are somehow applying a ridiculous amperage. That is 1 million amps. That is 1 million coulombs for every 1 second. I'm not sure that this is a real question, real scenario, but let's just keep going. So it's 1 million coulombs over seconds, or in 1 second there's 1 million coulombs. So I wrote it the second way. I said for every 1 second there's 1 million coulombs, so I could calculate how many seconds. That would be 7,940 seconds, which is a couple of minutes. How many minutes would that be? See, 7,940 divided by 60. It's 132 minutes. It's about 2 hours. 2 hours and change. That's assuming everything worked perfectly. This is theoretical. This isn't reality. But all the theory here, also I'm kind of curious as to how you're applying 1,000 amps. I'm not sure. But mathematically that works out okay. We changed mass to moles. Moles to moles of electrons, Faraday's constant, and then amperage. And those 2 things at the end are really the new ones. Faraday's constant being used, amperage being used. On the back, a steady current of 1 ampere is passed through an electrolytic cell, meaning everything's going backwards, containing a 1 molar solution of silver nitrate, having a silver anode and a platinum cathode until 1.5 grams of silver dissolves. If this was a galvanic battery, what voltage would be observed? Well, so in homework questions, in this particular homework question, I'm expecting you to go look up values in your textbook. So I went to the textbook or to the internet or something like that, and I looked up the two reduction values for this question. I looked up silver gaining electrons versus chromium gaining electrons, and so the the silver needs to be flipped to match with this equation up here, and so we have a voltage that is negative 1.74. Hey, Mr. Murphy, you said we're not supposed to have a voltage of negative 1.74, of negative values at all. Yes, I said that reactions don't work when the voltage is negative, but what if we're doing an electrolytic cell, meaning we're applying voltage? Do you have a question? You good? Okay. So, sorry, I just recorded that odd moment. So this negative voltage could be overcome if someone's applying an external voltage that's greater than it, which is what question B is about. So, hey, this is an electrolytic cell, meaning we're forcing a reaction to go backwards. This reaction doesn't want to go the way it's written. That's why the voltage is negative. But if we apply a voltage that's greater than that value, we can force our reaction to go backwards. Number C, how long does the current flow to obtain this deposit? So they obtain 1.54 grams of silver. So 1.54 grams of silver, that's 1 converted to moles of silver. And then for every 3 silvers, there's 3 electrons. Why not just write 1 to 1? I'm trying to follow the balanced reaction that was up here. Every 3 silvers, there's 3 electrons given off. But yes, you could write a 1/1 ratio there. And then for every 1 mole of electron, 96,485 coulombs. The amperage was 1, which is still very high for amps in regular electricity. And you go to your physics teacher, the amps are always pretty low here in school. But if you go into industry, they may have thousands of amps. Here we're dealing with 1. We get the amount of time it would take, 1,377 seconds. At the same time that this silver is reacting, chromium is also reacting. The silver is depositing, ergo the chromium is dissolving. And there's 2 ways to do D. Let's do D with the old school stoichiometry. That almost all rhymed. That was fun. Let's complete D using old school stoichiometry. So for every 1.54 grams of silver, convert that to moles. 3 silvers for every 1 chromium. 1 mole of chromium is 52 grams. 0.247 grams of chromium. Yay! That's using old school stoichiometry. Let's do it the other way. For 1,377 seconds, we're going to let this current flow. What current? 1 coulomb per second. Oh my gosh, a coulomb per second. Yep. 1 coulomb can be converted to moles using Faraday's constant. Now we know moles of electrons. There's 3 moles of electrons for every chromium, and for every chromium there's 52 grams. Also 0.247 because math. It's one of my favorite wrong answers you guys write down. Every once in a while you just write because math. That's happened a couple times. But you actually need to show the work to be able to write because math. So just doing stoichiometry, careful dimensional analysis. We have those 2 new things going on. We have the use of Faraday's constant, and we have the use of current as a ratio. Remember, current is the charge per time. This equation is given on the equation sheet. I'm using it right here, inverted actually, using the T over the Q, but using the units. Number 20. Calculate the delta G. Yeah, let's see if this thing's spontaneous or not. 1/2 cell electrochemical cell is made by placing a strip of zinc in zinc chloride. The other half, copper and copper nitrate. Calculate the initial voltage when the two cells are joined by a salt bridge. So we need to go find the values, because this is homework. I would give you a sheet of values for the test. So I looked up the two voltages. They were 0.76 and 0.34. So the combined voltage is 1.10, just like one of the examples in the notes. Calculate the final concentration of copper ions in the cell described in part B. This is part B. Looks like a typo to me. If the cell were allowed to produce an average current of 1 amp for 3 minutes. So 3 minutes and 13 seconds is really 193 seconds. Here's my amperage written as coulombs per second, converting coulombs to moles, and then moles to moles of copper. So here's where people get confused. After 193 seconds, 0.001 moles of copper have reacted. So these moles of copper are no longer aqueous, they are now solid. They used to be aqueous, but now they're solid. So after 3 minutes and 13 seconds, this many moles of copper have converted or reacted. So how many moles of copper did we have initially? Initially, we had a 1 molar, let's find it up here, we had a 1 molar copper solution, and it was 500 milliliters. So 0.5 molarity is moles over volume, so 0.5 times 1 gives me how many moles of copper were in there. And then we're losing, remember we're losing this many copper ions. So 0.5 moles of copper started, we lost 0.001 divided by the volume. And so this is really silly. It is now 0.998 molar. It dropped 998? Oh, yeah, because we're dividing it by 0.5. 0.998 molar. So the molarity did drop by 0.2% after all that time, after 3 minutes. It's pretty exciting. Actually, it would be pretty neat. You might not see that. One idea I have in our lab is to, actually figure out create a known molar solution, let the battery run for 5 or 6 minutes, and then test the molarity after that. But since the changes are so little, it's really difficult to actually do. And this is a small change with a coulomb per second. That's a big amperage. We're not going to get that many amps in our lab. Because we don't get many amps, we wouldn't see much change, so we wouldn't actually be able to measure the change in molarity, unfortunately. Wish we could, but we can't get our amperage up very high. Number 21. Determine the standard electrode potential for the reduction reaction. So this is like with an unknown metal. So we know the voltage of the cell is 0.740 volts. That's the voltage for the whole cell. So if you compare copper to this unknown metal, we should be able to figure out the unknown metal. So I looked up copper. This is copper's value, 0.34 volts. And so the total, this is the total, is the copper plus the unknown metal. So I'm solving for the unknown metal, which is 0.40 volts. And if I wanted to, I could probably figure out what the unknown metal was just by looking it up on a sheet. This is a pretty simple way of identifying an unknown metal, by looking up its voltage. Sure, you could look up the color of it. Like, what color do you suppose cadmium is? Like, if you had a metal in mind, what color would you suppose cadmium is?
Gray or silver.
Yeah, cadmium is generally gray. Good job. Good job. Very proud of you. Have a good weekend. So we could just find the voltage of this mystery metal, and then look up voltages on that reduction list, and then we would kind of take a decent guess at what the metal was, and we could do further tests with like solubility and things. So part B. Nope, that was all Part A still. Part B, a cell is constructed. Describe what occurs to the concentration of each ion as the solution is discharged. So as the reaction progresses, the copper ions become solid, so their concentration decreases. As the reaction progresses, the cadmium ions start being produced, have a good, and that means that their concentration should increase. How does the ratio of cadmium to copper change during discharge? Well, right now the ratio is probably 1/1, but as it discharges, the value of the cadmium should increase and the value of the copper should decrease. Therefore the ratio slowly increases, and it would keep going until it reached the equilibrium constant. And guess what happens when it reaches the equilibrium constant? The reaction stops and the voltage is finally dropped all the way to 0. Alright? You might not be at 0 molarity and max molarity for the other solution when it reaches equilibrium. Just it can't pull electrons through the wire anymore. 22. Explain each of the following. This is interesting. When an aqueous solution of sodium chloride is electrolyzed, Cl2 is produced at the anode and no sodium is produced at the cathode. How weird. So, wow, we have a very amazing drawing over there on the right with a 9-volt battery. I can tell it's a 9-volt battery because it's clearly labeled with all 9 volts right there. And 2 wires sticking in a salt water solution. And what a lot of people automatically think is that as the electrons are leaving the 9-volt and going in, that the sodium should be gobbling up those electrons. But we don't see any evidence of that because we don't see any sodium. We do see chlorine gas being produced, so the electrons that are being removed must be coming out of the chlorine. But what actually happens is there's also water in play here, and the water naturally ionizes into hydrogen and hydroxide, and we want whichever element is the best at gaining electrons to gain them first. So between sodium and hydrogen, hydrogen is higher on the reduction potential chart than sodium. So we see bubbles of hydrogen in chlorine, which, yeah, we could capture the 2 gases, and in capturing the 2 gases, we'd have hydrogen and chlorine mixed together, and if we lit them on fire, we can make hydrochloric acid, the gas. So the reason we don't see any sodium at the cathode is because we see hydrogen produced there instead. It's pretty cool. It's a better reducer. Number B. Letter B. The mass of iron produced, 1 Faraday, like that many coulombs, to reduce a solution of iron sulfate is 1.5 times the mass when 1 Faraday is produced iron chloride. Well, why would that be? Iron sulfate, that's iron plus 2, versus iron chloride is iron plus 3. So that is a 3:2 ratio, which is also a 1.5 ratio. So it takes 1.5 times the amount of charge to produce the same amount of iron. Right? Because it's a 3/2 ratio. We're talking a charge ratio, comparing the iron in the iron chloride to the iron in the iron sulfate. It would take more electrons to get the same amount of iron because of the difference in charge. Part C. The cell that utilizes the reaction above has a higher potential when zinc is decreased and when lead is held constant, but a lower potential when lead is decreased and zinc is held constant. Again, we're just explaining why. This is a Le Chatelier's question, really. If you add reactants, you increase the potential to shift towards the products. And that's what we want to happen. We want reactants to turn into products. That's what our voltage represents. If we increase reactants, we will see an increase in potential or voltage. If we decrease reactance, we see a drop in potential or voltage. Everything I just said, but in reverse when talking about the products. Increase products, that's bad, voltage drops. Decrease products, that's good, voltage increases. Part D. The cell utilizes the reaction given in C has the same potential as another cell in which zinc and lead are both 0.1. Usually we have a 1-to-1 ratio initially, but a 1-to-1 ratio is the same as a 0.1 to 0.1 ratio or a 2/2 ratio. As long as the molarities or both of them are the same, then we're in the same position on the equilibrium distribution, because it's products over reactants. We usually start with standard cell concentrations of 1 molar and 1 molar, but the difference by changing the molarities is the amperage. So which one do you think would have the highest amperage? Would 2/2, 0.1/0.1, or 1/1 have the highest amperage? Yes, you in the back with the funny looking hat. Yes, the one with the highest amperage would be the one with the highest molarity, because the higher the molarity, the more collisions per second. More collisions per second is more reactions per second, is more charges per second. And rate is impacted by molarity. Increase the molarity, increase the rate. Amperage is really about rate. Voltage is not. Number 21. This should be 23. Don't know why it says 21 on my page on the screen right now. Also known as the last question. A galvanic cell is constructed using a chromium and copper and chromium blah 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 blah. Write a balanced net reaction for the spontaneous reaction that occurs as a cell operates. So I went out and I looked up the values online, and when you look up the reduction values online, you see this one's gaining 2 electrons, this one's gaining 2 electrons. So these are the values I looked up online right here, and I have a negative and a positive value. One of them has to be flipped around. We're going to flip the negative one around, so we end up with a positive 0.17 and a positive 0.34. Adding the two reactions together gives us the total voltage. I obviously don't have that written up here. What would the total be? 0.34, 0.37, 0.51 volts would be the total voltage when you combine these two together. And write the reaction as it is in part A. We have a balanced net reaction, 2 electrons, 2 electrons. The copper is solid on this side, aqueous on the other. The chromium is solid here, aqueous on the other side. Draw a diagram that includes, and so I've got my little really bad diagram here. Let's zoom in on it quite a bit. So the copper is the cathode. Let's mix some water. This is the copper, it's the cathodes. The electrons are coming in here. So the electrons are flowing this way. It means that if the electrons are flowing this way, then the anions, so we're throwing through the salt bridge that way, back in. Oh my gosh, that salt bridge doesn't even make it in the beaker. This is a horrible drawing. Let's just make the beaker magically bigger. Who drew this? There we go. Fix this beaker up. Be nice if you could just stretch glass like this. And also, shouldn't that U-tube be in solution? There it is. Great. And it's all connected. Salt bridge is the orange thing. This is the anode on this side. This is where we're losing electrons, because the chromium is becoming chromium plus 2, right? So we're losing electrons here, and as we lose electrons, these chromiums are becoming chromium ions in the anode. I don't think I answered all the questions there. That's weird. Oh, part C. How does the potential of this cell change if the concentration of chromium is changed to 3 molar? If I change the chromium, which is a product, to 3 molar, then the voltage should drop because we're adding a product. That would be a bad thing. Remember, all of these are going to keep running until equilibrium is achieved. The farther away from equilibrium you are, the higher the voltage. But you add product, you might actually be past the equilibrium point, and it would have to shift in reverse, which means the electrons would be flowing backwards, and that's not good. Here is an example of a demonstration I'm going to do in class. We'll talk about that next time. All right. So practice, practice, practice. Think, think, think.